Welcome to this brief video on composite design in Tekla Structural Designer. Composite design has never been easier with our automated process, easy modeling, and review tools. To introduce this topic, we'll start with this model where the grids and columns have already been created. I've set up this building so my second and third floor are duplicates of each other. That way only one floor needs to be modeled. The 3D view and second floor plan can be opened side by side to see the building coming together as you model. In this template file, there are several sets of properties saved that will allow us to quickly model the members. Your company can create these properties based on your projects and typical beam types. You can always add more to these and modify them as the project evolves. By selecting a predefined set, I know all the properties for this beam are set up the way that I need them. For the perimeter beams, I'll choose a composite without camber set. Let's take a moment to review the properties. The construction type will define if this is a composite or non-composite beam. TSD assumes an unshored construction for composite beams. For the pre-composite design, we can choose to let the program define the top flange bracing for lateral torsional buckling based on the deck orientation relative to the beam. If the deck is perpendicular to the beam, the top flange will be continuously braced. If it's parallel to the beam, the top flange will not be continuously braced. For the parallel option, the beam will be braced automatically at locations where other beams frame into this one. For the post-composite stage, it's assumed the slab fully braces the beams. Next, we can define deflection limits. These can be set up for individual load cases with their own relative limit, such as L over 600, or absolute value, such as 0.375. If both of these are turned on for a given load case, the program will design to the worst case. Simply check the box on or off to control whether a load case will be checked for deflection against the allowable or not. Then input the values as appropriate. You'll see for this property set, camber is turned off. You can set size constraints for max, min depth, and width of beams. Next, define the stud strength for a composite slab. Review and modify these properties as needed for the given project. The Optimize Shear Interaction option will be on by default. If you turn this off, the beam will be designed to 100% composite action. The percent composite action is defined via these two minimums. The program will design the maximum moment of the beam to the absolute minimum. However, you can choose to have the program warn you if this is lower than some advisory minimum you would like to consider. The program will also check critical points along the beam and if their utilization ratio is higher than at the maximum moment. For example, if you have high concentrated beams or loads located near the end of the beam where the number of studs are lower and therefore the percent composite action is lower, the utilization ratio could become more critical. TSD will flag these conditions for you so you can review them and decide on how to proceed. The connector layout allows you to define how the shear studs will be laid out along the beam. A non-uniform layout means the stud spacing can change along the beam, so it can have tighter spacing at the ends and larger spacing along the center. A uniform layout would maintain the same spacing along the entire beam regardless of what may be required at specific locations. The entire stud spacing will be based on the worst case and evenly spaced. You can also set several max-min options and select to keep the studs symmetrical about the center of the beam. Now I'm ready to model those beams. These are going around the perimeter. I can draw windows around my exterior columns to quickly lay out these beams. Next are the interior girders along column lines. For these I'll change the property set to composite beam with camber. Most of the properties here are the same that we've already discussed except for deflection and camber. Under deflection, I've turned off the dead load check. This will be considered under post-composite when both dead plus live post-composite loads are considered. For these beams, the camber check is turned on. Camber can be applied as a value, proportion of span, or proportion of dead load. If dead load is selected, you have the option to select the slab only or all dead load. The specific dead loads considered are controlled by the load combination selected for camber. You have control to indicate if dead load is pre-composite or post-composite by selecting the appropriate combination. You can see for my project I've selected the construction stage combination to define camber. I'll use this property set to generate the rest of the beams. This is accomplished quickly by drawing a window around all columns. Then, using the infill beam command, we can quickly place 3 evenly spaced beams using our pre-saved property set and placing them in every bay. Once the beams are in place, I can add my composite slab. I've already saved a typical composite slab in the property sets. This is a 5-inch total slab, 2-inch deck plus 3-inch concrete topping. Within the slab properties, we have a factor that will impact the deflection calculation for composite beams. That is, this short-term and long-term elastic modulus. TSD applies a divide by factor to reduce the short-term elastic modulus by this value to be used as the long-term modulus. This is done to consider shrinkage and creep in the concrete. The program will use the appropriate modulus, short or long term, to calculate a corresponding modular ratio. It then uses the appropriate ratio for a given load case to calculate the deflection. If you do not want to consider shrinkage and creep in composite beam deflections, you can set this variable to 1. Modeling the slab is as quick as drawing a window around the entire floor plan. Now, in order to actually get the beam designs, I'll have to quickly add some loads. So I'll just add a level load over the entire floor plan for dead, live, and construction live. Before running the design, I'll open the Show Process window. This will indicate each step as the program works through the analysis and design. Once done, it will show any warnings or errors or indicate a successful completion. Click on Design Steel Gravity to now run through a gravity design. All my beams are set to auto design, and the program will perform an analysis and optimize the member sizes and shear studs. Once done, we'll see color-coded the pass-fail warning results for all members. We can also review the ratio color-coded to see by how much the members are passing or failing. We can review the results by right-clicking and looking at the design results. Here you can quickly see a summary, but also dig deeper into individual checks and the controlling load combinations. The screen will show all calculations and code references as applicable. Double-clicking on the beam, we can quickly review the stud layout. This is a great way to see how the studs are laid along the beam. Here you can also change the stud arrangement and quickly regenerate it. You can then redesign the single beam to see if this new arrangement still passes all of the checks. Finally, we can also right-click on a beam and look at the load analysis view. Here you can view the force diagrams for the individual beam, both by extremities as shown in the diagram, or at specific locations along the beam. We can also change back to a regular floor plan view and turn on the text to see the section sizes, the studs, and any camber on all of the beams. That brings us to the end of this brief introduction to composite steel design in Tekla Structural Designer.